Hello my dear friends and welcome back to AdBlock. In today's video I continue the reparathon of the 24V to 230V inverter with some special fireworks at the end. I pick up right where I left off last time. The input stage had no problems. Once the right signals were applied, the DC link capacitor could charge up to 400V. The real issue was with the gate driver board and the 4 MOSFETs of the output bridge. In the last episode I tried to patch it up, even adding an external microcontroller, but today I'm starting fresh. I strip everything down and I check each single components one by one. I lost the count of how many times I removed that little PCB with the drivers. And got it! Once again, one gate driver is shorted, while luckily the other still works fine. So I desoldered the faulty chip and soldered in a new one. And with the LCR meter I checked all the capacitor, especially the bootstrap ones. And each capacitor reads about 20 microfarad, exactly as expected. Then, with some dedicated hand soldering, the new gate driver is in place. These are the last gate drivers and I'm not going to buy new ones, so cross finger for the repair. Testing the signals, everything looks perfect. Around 13.3 volts on the high level at the output. And one problem is solved. And now it comes the software. The microcontroller and Arduino Nano runs a code base derived from my old 3-phase inverter project that you may have seen on my channel, with a touch of AI, since nowadays it's kind of everywhere. I'll share the code at the end of the video and on my socials like Telegram and Patreon. After a little tweaking, I finally programmed the board and look at this beauty, a clean sinusoid already filtered. With the oscilloscope I can zoom in on the PWM signal, 31 kHz, and there it is, the full sine wave. The exciting parts, since I wrote the code myself, I can adjust both the amplitude and the frequency of the generated signal, a feature you won't find in off-the-shelf inverters. Now that the microcontroller works, I move on to reassemble the main board, and unfortunately all the soldering and desoldering damaged some pads, unlike high-quality boards from JLCPCB. They are professional PCB manufacturer offering 5 pieces, 2 to 6 layers starting at just $2, with blazing fast 24-hour production. Upload your Gerber file, get an instant preview and a quote, and very soon a nice package with your PCBs arrives at your doorstep. I often rely on JLCPCB for my AdBlock projects. You'll find the link in the description with a discount code to support the channel. And back to the repair, and then one important solder pad lifted. So I had to fix the trace with a bit of rigid wire and some magic, before cleaning everything with isopropyl alcohol. To my rescue comes RS Components, sending me 30 brand new 600V 120A IGBTs. Real beasts, FG860 and 60 SMD. Once again, I solder them back to the board, connect the control module and prepare for the final test. This time, to measure the voltage with the oscilloscope, I had to use a differential probe as the bridge output comes from switching devices, and 2 power supplies, one powering the driver board and another in the inverter DC bus. Powering the first, gate signals appear at the oscilloscope. Then I feed the inverter bridge. And there it is, a perfectly smoothed sine wave, and look at that! 50 Hz confirmed with a 30V peak-to-peak at the output after filtering. Look into detail, you can clearly see the PWM modulation, a square wave at consistent frequency and duty cycle varying sinusoidally. Filtering it out produces the pure sine. For this test I only gave about 20V at the DC link, but now it's time for the real deal. 24 volt input at the inverter to get over 400 volt at the DC link. Everything is wired up, and here I'm a bit nervous. Here we go in 3, 2, 1 and nothing happens, damn! The small power supply hits the current limit at 5 amp. That must be it. And tired of waiting, I connected the inverter straight to the batteries, 212 volt 100 amp hour in series. Electronics really eating up here. In 3, 2, 1... And you see the sparks? They are normal, charging all the input capacitor of the 24 volt line. And ready for the test. Oscilloscope on, switch on in 3, 2, 1 and... Oh my god, it works! Finally the sinusoidal wave is here! And the inverter draws about 7 amp, which explains why the PSU tripped. But suddenly, bang! Here something blows up, and looking closer, one IGBT is shorted. But the real damage seems to be the shunt resistors, burnt black. Even the Arduino microcontroller died in the blast. Still, the rest of the board powers up, and the display lights. Auxiliary voltages are fine with the 5 volt, and fortunately for me, the DC link runs about 385 volts, close enough to 400. To load the DC link, I grab my trusty old-school resistors, dusty but reliable, about 1 kilo ohm and 100 watt of electric load. I hook them up and activate the system again. And look, 407 volt at the DC link, drawing over 5 amp from the battery. The resistor eats fast, but the inverter circuit holds steady. So why I should keep the DC link only? Because of this brand new board I designed, a full bridge converter with 4 MOSFETs or IGBTs, meant for a microcontroller driven single-phase inverter. I will cover it in a dedicated video on the channel very soon. For now, the key takeaway of this video is the code, Arduino firmware generating a clean sine wave adjustable both in amplitude and frequency through PWM modulation. The code starts from macro definitions. PWM pins are a 256-point sine wave table, therefore an array, and a max-min duty cycle range. The setup configures timer 1 at 31 kHz PWM output and a timer 2 as internal interrupt. The timer 2 interrupt service routine updates the duty cycle at fixed intervals, cycling through the sine wave array, while the main loop reads potentiometers for amplitude and frequency adjustments. And that's it for today. The next video will dive deep into the new board design, its schematic and the code itself. Don't forget to drop a comment if you have any question. And of course visit my social media like Patreon, Telegram, Instagram and Facebook for project updates and extra materials. And of course hit the notification bell if you enjoyed this repair adventure. See you soon on the ATLab channel. Ciao!